So let us start into this lecture today, and as the content in this lecture I have told you that we will be having a recapitulation of all the previous lectures. So starting with lecture 1, we have seen the course objective, course outcome. You can see it, course objective, course outcome, syllabus we have seen, introduction to the course and brief introduction to the unit 1, that is microprocessor 8086. So the course objectives are here to get familiarization about the 8086 microprocessor and 8051 microcontroller. That is what we will be checking out in the first 2 units. In the third unit, our objective will be to learn the interfacing techniques of microprocessor and microcontroller based systems, their communication strategies, bus and memory interfaces also we will see. And unit 4 and 5 talks about the ARM architecture and the modern day available ARM devices in the market. The outcomes of the course are again the things what the objectives point to. The outcomes, we expect that the students understand the internal architectures, understand the different programming ways of the microprocessor and microcontroller 8051, most basically the assembly language programming way. Okay, and we also need to check it out. The student gets the understanding about the different interfacing techniques in the microprocessor and microcontroller based systems. Okay, and finally the student should also understand the latest RISC architecture in the ARM processors and to get familiarized with the basic concepts in the latest advanced ARM processors. In syllabus, we have seen that the unit 1 consists of the 8086 microprocessor and all the related things about it. Its internal architecture, okay, its assembly language programming and all. Unit 2 talks about the microcontroller, specifically 8051 microcontroller, which is a 8-bit microcontroller. Okay, all the certain things about the internal architecture, programming and all what we have seen for 8086 in the unit 1, we shall talk about the such similar things about the 8051 in unit 2. Unit 3 is about interfacing different IO interfaces and memory interfaces and the serial communication interfaces into the 8086 and 8051 systems. Unit 4 is giving you the basic understanding about the RISC architecture in ARM processors, and Unit 5 is talking about the basic concepts in the latest available advanced ARM processors. Okay, we have checked out this basic block diagram in the computer. What does a computer contains? It contains input devices, output devices, and a CPU. And always, sometimes we consider the memory as a part of the CPU, but it is not the case in the terms of microprocessor-based systems. In microprocessor-based system, the memory is connected externally. Okay, like this. So internally, what only we have in is a microprocessor is ALU, control unit, and a register array. All such things we have seen in the architecture of the 8086, and specifically the register array we have discussed in the register organization of 8086. Okay, I have shown you the different images to get familiarized with the what exactly a microprocessor and microcontroller means. I am definitely sure that you might have seen these things in the real life by yourself. The processors, the latest versions, Intel i7, okay, and the microcontroller 8051. So it is particular 8051 microcontroller, but in a version 8089C51. Okay, and that one is the Arduino, and here we have the 8051 development board. Okay, and these two images from now, this one and the next, gives you the understanding the difference between the microprocessor and microcontroller devices. Whereas the microprocessor contains a microprocessor only, control and arithmetical logical units, and whereas a microcontroller contains the control unit, arithmetical logical unit. Along with that, when it contains the timers, memories, clock, IO interfaces, and many other peripheral devices on a single chip. Again, they are limited in number, so it limits its efficiency. Whereas in microprocessor-based systems, as that restrictions are not there, it is a very multi-purpose device used for many multitasking operations, and its efficiency is very high. Although here the limitation is that you have to interface all the devices required for a fully system functioning from the external sources. Okay. So even this image shows you the difference between a microprocessor and a microcontroller based systems. Here, the unit 1 talks about everything about the 8086 microprocessor. It's architecture, instruction set, and assembly language programming. We have almost done with the architecture of the architecture part of this unit, because we have seen architecture, we have seen the register organizations, and we are dealing with the memory segmentation in 8086 systems. Later on, we'll be checking out the programming model and continuing into the addressing modes and instruction sets of 8086. And finally, we'll be understanding and writing few assembly language programs also about the 8086. So this is a basic definition of a microprocessor. You should be very comfortable with this definition, because I hope you already know the IC definition. Integrated circuits definition is that it's a semiconductor IC on which the many transistors are fabricated in a bulk number, such that it functions as a one particular digital circuit. Similar thing, when that particular digital IC is a program controlled, that means you can control the tasks, operations of that IC using a program which you can write on it. So that type of devices are the microprocessor devices, and basically they are used as a CPU in the computers, all our desktop and laptop computers. So here we have talked about the different generations in the microprocessors. Specifically, we'll talk about the Intel only, because we are studying the Intel's 8086 processor. So all things started in the 1971, okay, when the first release of 4004 4-bit microprocessor was released. And after that, it's a history. We have seen this. In second generation, we got this 8085. In third generation, we got this Intel 8086. And after that, the later versions we have seen in the fourth generation and fifth generation. For your knowledge, currently, Intel has recently changed its logo also updation 2 days back. They changed their logo, and along with that one, they released the first feature release, that means feature listing of their 11th generation processor. It is a Core i9 X series 11th generation processors. They have released it. Just the features of it. Maybe in some time we'll get that device also into the market. Previous versions of i9 Core are available, but they have brought some new thing into the latest Core i9 X series processor. 2 days back, you can find in the news. Okay, we have seen this all different generations. First generation, second generation. Okay. First generation is this. Coming to the second generation, we have it here. Third generation of the microprocessors, in which 8086 is very commonly available, and it is being discussed all through our Unit 1. In fourth generation, we got this Intel's advanced version in the 8086 family, that is Intel 80386. After this, 486, 586 also came in the same 1980s duration. And then the Pentium came and everything changed. We know from the Pentium onwards, the processing speed is tremendously increased. Okay, we got this Pentium series, Xeon series, Celerion, Itanium, Core 2 Duo. Okay, and the now Core i series, in that one i3, i5, i7, and currently the i9 is the in the development phase. The next versions of i9s are in development phase. Yeah. In Unit 2, we have discussed the features of 8086 and architecture of 8086. So features of 8086, let me list it out quickly again. So in features of 8086, it is the first 16-bit microprocessor released by the Intel in the year 1978. Okay, and its fabrication technology, what it was used is HMOS. HMOS, for your understanding, you already are comfortable with the term CMOS, I guess. Okay, so HMOS is hybrid MOS, in which CMOS and TTL logic families are that means combined, or the benefits of these two features are taken into in a single fabrication technology. Hybrid MOS technology it is. MOS, I guess you know, it is metal oxide semiconductor devices. So then we got this in this. It is a 40-pin dual inline package with the 5 volts power supply, workings up voltages 5 volts, and on this particular IC there are 29,000 transistors fabricated. Onto the IC maybe of 2 or 2.5 inches in length, okay, and maybe ½ inch in the width. And it does not have any internal clock. You can provide an external clock triggering to synchronize all its operations in the microprocessor based system. You are quite aware about the sequential circuit, synchronous sequential circuit. So our microprocessor based system will be the synchronous sequential circuit. It requires a clock such that its internal and external operations for whole system operations can be synchronized. So here the requirement is that you have to give an asymmetric clock source with a 33% duty cycle in this. And about the duty cycle, you know, it's on time by total time of the clock. So here we are having the 20-bit address lines, or that means 20 address lines are there in 8086, such that it becomes the memory addressing capability of this device as 2 power 20 bytes. So 2 power 20 bytes is 1024 kilobytes. 1024 kilobytes is 1 megabyte of a memory capability is there, memory access capability is there in the 8086 processor. That means you can interface in memory to this processor as 1 MB up to 1 megabyte of memory. Okay, it seems to be very small in the common days of terminologies, but in 8086 based system, it's a very much sufficient memory available. Then we have talked about its memory addressing space that is actually of total 1 MB, that is total 1024 kilobytes. Again, this 1024 kilobytes is divided into two banks. They are called that is even bank of memory and odd bank of memory. Two different physically separated ICs will be there of 512 KB each. One bank is called as 512 KB and even bank, and other is called a 512 KB odd bank. About this one, just after our memory segmentation discussion completes, we'll talk about in further detail, and more clear understanding we'll get it when we talk about the 8086 signals. Okay, it uses a separate 16-bit addresses for the IO devices. Sometimes 16 bits and sometimes 20-bit address also it uses for the IO devices. And addresses are required because it has to know from where it is accessing the data or giving the data back. So getting the data into the processor or sending the data back to the devices, maybe the memory or IO devices. So for that one, addressing should be known. About this particularly, how the address calculation is done, we have seen in our recent class. So it operates in two modes of operation, that is it can work in two different modes. One is called minimum mode, other is called maximum mode. What these modes are, slowly we'll understand. Briefly, I'll give you the understanding here is that minimum mode is a single processor based system mode, where in a system, in a computer, only one CPU will be there. Only one 8086 CPU will be there. Whereas when you configure this 8086 in maximum mode, in one computer, you can have more than one CPU. So it works as a multi-processor based system where you can have more than one 8086 processor in one computer. So parallelly, they work such that the speed of the operations of that system can further increase. So minimum mode, one processor system, maximum mode, multi-processor system. In one computer, more than one CPU. So after that one, we have talked about the 8086 architecture. In architecture, we have seen these two units, bus interface unit and execution unit. Again, internally, as a whole, it is one thing, but internally it works as two different units. These two different units, that is bus interface unit and execution unit, works simultaneously, independent of each other's activity, such that the whole processing speed increases. Okay, while the job for the bus interface unit is to fetch the instructions into the processor, to get the instructions and data from the memory and IO devices into the processor. It does that thing, and the job of execution unit is to take those instructions and data and decode those instructions and finally execute the given instructions according to the program instructed to it. Okay, that is about this bus interface unit and execution unit. More specifically, the three quantities are there in the bus interface unit. We'll see in our next few slides. So bus interface unit, what it does is it fetches the instructions, read the data from the memory and IO devices, write the data to the memory and IO devices. Whereas execution unit work is to execute the given instructions by first decoding them, obviously, and which are already fetched in the bus interface unit. So execution unit basically decodes and executes the instructions which are pre-fetched by the bus interface unit. Address is equal to segment address into 10 plus offset address. So about this whole formula only, even with examples also we have seen in our previous class. This queue is of 6 bytes here. So it can pre-fetch the instructions of the program. Up to 6 bytes of instructions it can pre-fetch, such that while the processor execution unit is executing the instructions, it can just fetch the next instructions out of it. Okay, so we got this bus interface unit and execution unit into it. So they work separately, individually. Okay, that's very important point. They work individually and separately. So far, in the previous two lectures, what we have discussed, even in this class, is that about the course introduction, objectives of the course outcomes, syllabus, how it is framed, what is each unit about, and after that one we have gone into the 8086 introduction, when we have seen its features, followed by its architecture, and now in this unit we will be continuing our discussion of architecture, individual blocks in that bus interface unit and execution unit, and after that register organization is what we will be revising. So here is the bus interface unit. It contains a major three things. Okay, it has an address generator. The job of this address generator is very clearly we have discussed in our previous class while talking about memory segmentation, that here 8086 can address up to a 20-bit locations of address, but whereas it has only a 16-bit registers inside it. So to deal with this, what it does is that it cannot hold a 20-bit physical address into any of its internal register. So what it does, it takes the address split into two quantities, which is called as a segment address and offset address. Together they are called as logical address. So segment address will be actually your top 16 bits of the segment starting point. Okay, when we take in hexadecimal numbers, the physical address will be of a 5-digit hexadecimal number, whereas the 8086 can hold only 4-digit hexadecimal numbers in any of its register. So top 4 digits of the segment starting address will be there in the segment register. It can be a code segment, a CS register, DS register, ES register, and SS register. Okay, they will contain, or any one of these 4 contains a segment address, depending upon you are accessing the code or the data. When you are accessing code, means program instructions, that time CS will hold the segment address and IP will hold the offset address. When you are accessing the data, depends upon what type of data it is. It is a random data, normal data, that time the DS, data segment register, will hold the segment address, and SI generally will hold the offset address. And in some cases, ES, extra segment register, will hold the segment address of the data, and DI, destination index register, holds the offset address of the data. And finally, the stack segment of memory, when it is used, that means wherever you are accessing the data which is in stack format. Stack format, again I can tell you, normal data formats here is the random arrangement. When anywhere it is there, anywhere you just go and just take that data and come back. But in stacked data format, it is not like that. The start data is placed one over the other, okay, as a stack of books in the shelf or something, where you can just access the topmost of it at that moment. So it will be a last in first out type of an organization, where you can access the last entered data at the first point. Okay, there are the two types of arrangements actually. Stack is one arrangement, and another is arrangement is called queue. In queue, whichever you entered first will exit the first, okay, or whichever you entered the last will exit the last. So these two type of formats of arrangements will be there. In memory, we have the arrangement of the stack data, but in bus interface unit, we have one queue also available, in which the instructions are pre-fetched for ease of access. Here, the instructions are pre-fetched in the format of queue. That means first instruction is fetched first, second is fetched next, third is fetched next, like that. And their exit from this queue will be first will go out, then second will go out, then third will go out, and like that, one after another. Whereas stack is different. Whichever enters last will be taken out first. Anyhow, this queue will be very helpful for pre-fetching the instructions, so that the ease of operation becomes easy here, or the working examples becomes very easy here. Bus interface unit contains instruction queue. About Q also I told you that they are used for pre-fetching the instructions such that the speed of operation increases. Okay, talking about the execution unit contains of, again, three major things are there in execution unit. That is a general purpose register set is there. Okay, AX, BX, CX, DX. Then we have it, this ALU, which is, you can say, has a heart of a microprocessor. Here all the arithmetic and logical operations and string operations are handled. Okay, the operations what the processor can do is the data operations. It can manipulate data by doing arithmetic operations on it, by doing the logical operations on it, and it can handle the string data by manipulating strings. Strings, when we say, it's a collection of characters, and here what manipulations in the string you can do, you can insert few characters into the given string, you can delete few characters out of the given string, you can compare two strings. Okay, these all things you can do with the strings. So about the general purpose registers, about the ALU, and about the what you can say, this is about the control system in it. This control system is responsible for synchronizing all the internal operations. It synchronizes all the internal operations. So it gives the control actions. That means which job has to be done first. The ALU operation or the flag indications and activation of general purpose registers and so on. Yeah, so now we are into this unit for the lecture 4 out of it. So far we have discussed the architecture in the previous unit. Here we will be talking about the register organization, how well the registers are organized, placed, where they are placed, what is the role of each register, what is the purpose being that register plays in the particular area of the architecture. Okay, that is what we will be going to check. So as you can see, and I have told you that there are total of 14 registers, 14 registers in 8086, out of which you can have a look about the 13 of them here, 4 as general purpose registers, AX, BX, CX, DX. Another 4 are segment registers, CS, DS, ES, SS. 4 is 8. Then we have 2 pointers, SP and BP, and we have it 2 index registers, SI and DI, and 1 instruction pointer. So 8 plus 2 is 10, plus 2 is 12, plus 1 is 13. And apart from these 13 registers, we have 1 flag register. Okay, 16-bit flag register is there. Obviously, in that 16-bit, we have only 9 active flag bits. So these 14 registers are there in the 8086. Out of these 14 registers, we have seen that 5 registers are the part of bus interface unit. They are in the bus interface unit, and those 5 registers are all your segment registers, CS, DS, ES, SS. Along with the segment registers, we have IP, instruction pointer, placed in the bus interface unit, and all the other registers are in the execution unit. As 8086 does not have a 20-bit register inside it, the address is actually placed or arranged in the form of logical address. Logical address is an arrangement in which you have your segment address 16-bit and offset address 16-bit, and you use that formula of segment address multiplied by 10h plus offset address to calculate your 20 bits of address location of your data or program instructions. So here the listing of all that categorization of registers here. So you can see general purpose registers are there. 4 of them are there: AX, BX, CX, DX. So you can see here at AX, BX, CX, DX. Here are the list of my registers, categories. General purpose we have it, then pointer registers we have it. There are 2 pointer registers, base pointer and stack pointer. Then we have index registers, that is source index register, and destination index, that is SI and DI. Then we have instruction pointer IP. We have segment registers, 4 of them are there: CS, DS, ES, SS. And finally we are having our the flag register, the flag bits. These are the categorization for ease of understanding. Segment registers, okay, general purpose registers, pointer registers, index registers, instruction pointer, and flag. Even though the instruction pointer is also pointer register, but we name it separately because it does does the job which is something different from others. The other pointer registers SP and BP are used for holding the offset address of data. Okay, data of the program, whereas this instruction pointer holds the offset address of the instructions of the program. Okay, generally a program contains instructions and data. These two things combinedly gives us the program, because when you are writing instructions, you are telling the processor to do something upon something. So what to do are called instructions. Upon what thing has to be done, that is called data. Okay, so you have to understand this one more clearly. Program is a set of instructions given to the processor to tell it what to do, and data is provided for the processor to tell it upon what it has to do that task. Okay, so it's about all the different registers here. Code segment register used for holding the segment address of program instructions. Data segment registers used for holding the offset address of the data. Stack segment register used for holding, not offset address, sorry. Data segment registers are used for holding the segment address of the data, not the offset address, sorry for that. Stack segment register used for storing the segment address of stacked data, stacked memory in which the data is placed one upon other. Extra segment is similar and kind of same as the data segment register. It also holds the address of the data which is randomly arranged, just as your data segment. So it's basically extended area for storing the data, where data segment of the memory is the normal area where the data has to be stored. This extra segment register or extra segment of memory is the extended area where the data can be stored. Instruction pointer, I have told you, for the logical address, one part is segment address which the segment register holds, other part is the offset address which the offset type of registers hold. Offset type of registers are all here, that is instruction pointer is there, index register SIDI is there, pointer registers, that is SP and BP is there, and in special cases BX is also there for holding the offset address. Now when this offset address is of the program instructions, okay, code, that time the instruction pointer register will be used. So it holds the offset address of program instructions and not the data. Okay, followed by this we are having the discussion of general purpose registers. Accumulator, generally it acts as an collecting point after doing any arithmetic and logical operations. Basically here is the default location for the result to be hold. Default location for the result to be hold. Accumulator, it accumulates the result basically. Base register, it's a type of register in which the data can be stored normally, general purpose, and the special purpose is that in the different type of addressing modes, specifically the addressing modes where it is named as based addressing modes. So we have base addressing mode, base index addressing mode. Okay, in those cases this register BX will also be used for holding the offset address of the data. These things will be clear to you when we discuss the addressing modes. Okay, we see go into the program structure, how the programs are written and how the data is accessed in the program. So there you will see different ways of accessing data. For brief example I can give you. Suppose if I want to have a communication with any one of you, I can call you directly by your name. Okay, this thing is you have understood in the C language. You can call the data by value. Call by value, and other way of calling the data is call by reference. So in call by value type of thing, directly you call the data by its value itself. So here that type of addressing is called immediate addressing mode. Okay. Then we have call by reference in C language. So similar type of thing here is that when you call the data by its not the actual value, instead where it is located, its location you use it for calling it that data into the program. That time in C language you call as reference, but here there are different terminologies that how the address is calculated. If the address is calculated in index registers, you call index addressing mode. If the address is hold into the offset address, obviously hold into the pointer registers or base type of registers, you call as the base addressing modes, and so on. Index addressing modes and base addressing modes are the more common of these two. Of the other type of call by reference type of calling in this assembly language. CX register is counter register. By default, it does counting operations. That means it counts that how many instruction bytes are executed so far. By default. Otherwise, you can use that one as general purpose register to hold the general data. Data register is again a general type of register only, but in some cases where suppose accumulation is not possible only in the AX register. Suppose multiplication operation, you are multiplying two 16-bit numbers. Multiplying 8-bit numbers will give you 16-bit result, but multiplying 16-bit numbers will give you 32-bit result. And job of accumulator is to hold the result, but the size is 16 bits, so it cannot hold the result which is 32 bits. In those cases, the DX will act as an extended hand to the accumulator. Okay, it gives an extension to the accumulator. So this also becomes a part of accumulator, where the lower result is stored into the AX register, higher result, lower and higher means the size 32 bits if it is there, 0th bit LSB to MSB 31st bit. In that one, 0 to 15 will be stored in AX register, 16 to 31 will be stored in DX register. Okay. Stack pointer and base pointer registers. They are used to point to the stacked type of data. Basically, these two are used for holding the offset address of stacked data. Okay, then we have this index registers SI and DI. SI and DI both are used for pointing to the random data. Okay, and in some exceptional cases of string manipulations, source index and destination index are very useful for indicating how the strings are manipulated. Where is the source of the string manipulation? Where is the destination of string manipulation? Especially in the case of string matching or comparison. It takes two different strings located at two different places. Source index points to the source of the string, source string, and DI register points to the destination string. And character by character, they will be matched and compared. So all the registers with their special functionalities you can see on this slide right now. You can see accumulator is there. It works as an accumulator for a 16-bit results to be hold of the arithmetic and logical operations. Then we have AL, the shorter version of the AX. AX is a complete 16-bit register, whereas AL is a 8-bit register. Then we have BX, CX, DX, SP, BP, SI, DI, all of them here. Flag register is there, bit 0 to bit 15. You can see bit 0 this side and bit 15 that side. Out of these 16 bits, we have only 9 active bits, other 7 are inactive and different flags are there. So when we start from here, it is carry flag, parity flag, auxiliary carry flag, zero flag, sign flag, we have it. We have after sign flag, trap flag, interrupt flag, direction flag. These 3 bits, 8, 9, 10, they are the control flag bits. Out of the 9 active flag bits, 3, that is trap flag, bit number 8, 9th bit, that is interrupt flag, and bit number 10, direction flag. These 3 are the control flags. That means these are program accessible. You can put some 0 or 1 into it and you can control the action of processor. Okay, whereas other 6, okay, that is carry flag, parity flag, auxiliary flag, zero flag, sign flag, and lastly overflow flag. These 6 are status indicators. They just show what happened in the processor right now. Status flags they are called. Okay, so in lecture 5 we have elaborately discussed about the different flag bits, and before that I will give you understanding about the data structure, 8-bit data, how it looks, 0th bit position to 7th bit position, total 8 bits will be there, and here it is having lower nibble and higher nibble, 2 nibbles. Nibble is nothing but collection of 4 bits. Byte is nothing but collection of 8 bits. Okay, and the last, so all the registers in our 8086 are this type of structure here. So we have 16 bits, 0 to 15. So bit number 3, whenever bit number 3 is generating carry or taking a borrow, that time our auxiliary carry becomes 1. It sets. Okay, so our 8086 data 16 bits have 4 nibbles. This is lowest nibble, and this side 12, 13, 14, 15 are the highest nibble. Okay, flag is this parity flag, auxiliary carry, 0, sign. Their names define their functions actually. Okay, carry flag is one thing. Suppose your arithmetic operation is generated carry from the MSB bit. That time carry flag will set. Parity will check the number of ones into the lower byte. Okay, into the bit number 0 to 7. In that one, it will count the number of ones. Okay, if the number of ones are even, it will make that one ought to become itself 1. So parity becomes 1 when the number of ones in the lower byte are even numbers. 0 flag is one in which it set whenever the operation of the ALU is 0. Okay, so when you subtract the same quantities, the operation output will be 0. When you decrement the numbers and when it reaches 0, the outcome is 0, like that. So all the status flags will be used for making our conditional jumps in the program. Okay, we'll make the decision whether to skip certain instructions and do certain other instructions. So these all status flags will be helpful for us for making decisions. Decision making in programming generally. So status flags will be used for that purpose. Anyhow, sign flag will show you the sign of the result, whether it is positive or negative. If it is 0, the result is positive. If it is 1, the result is negative. Okay. Then we have this trap flag used for controlling the processor execution cycle, whether it is a full execution or a step execution. Step execution means it will execute one instruction at a time. Interrupt flags are used for masking or ignoring or allowing the maskable interrupts, controlling the maskable interrupts basically. Direction flags decides the direction, whether it will be a program into the auto incrementing mode or auto decrementing mode, increasing order or decreasing order. Overflow flag will be setting whenever we have an arithmetic overflow occurring, binary overflow. Okay, binary overflow will be, suppose you are working with 16-bit numbers, you add to 16-bit numbers and you will get a 17-bit result. That is an overflow. So to indicate that one, overflow flag is placed. Okay, that is all about this flag registers. These all together here. So in our previous class, we talked about memory segmentation. We have seen the different types of memory addressing, that is linear addressing and segmented addressing. Okay, linear addressing is one whenever the complete address location you are indicating in single register of processor. Everything is there. That this type of case is available in 8085 register. 8085 register follows the linear addressing. It has 8-bit registers internally, and its memory addressing capability is also a 64 kilobyte. 64 kilobyte means 2 power 8 bytes. So 8 locations it can do it, and addressing is linear there. Linear means directly complete full address is available to in a single point. In segmented addressing, the address is split into 2 halves, 2 parts. Okay, segmented addressing 2 parts are there. That is called logical address. Okay, segment address, when it is divided into 2 parts and indicated, it is called logical address. In logical address, we have on the left hand side the segment address, then colon will be there. On the right hand side, we have the offset address. Segment address colon offset address is the logical address in the segmented addressing formats. So this is an example. This green color indications are here 20-bit address written at one point. This is a linear addressing. All the 20 bits are available at one point. So linear addressing. Whereas segmented addressing is this yellow thing here. Whereas you can see that 20-bit address is now not available as the 20-bit number at one point. Instead, it is available as a 2 16-bit numbers separated by a colon. Okay, this is called logical address. Segmented address are indicated in logical address, where on the left hand side we have segment address colons. On the right hand side we have the offset address. Okay, we have talked about the memory segmentation, and we have seen the advantages also of the memory segmentation. Why we have a 8086 having as a memory segmentation in its memory addressing. Advantages of that one we have seen. Overlapping type of segments and non-overlapping type of segments you can see here. 0 and 1 segments are non-overlapping, whereas segment 1 and segment 2 here are partially overlapping. Segment 2 and 3 are completely overlapping, like that. 8086 supports both overlapping and non-overlapping type of segmentation. Basically, the overlapping type of segmentation will save the memory, whereas your suppose given task program is very short. It don't require different complete areas of memory for storing your program instructions and data. In the same chunk of 64 kilobytes of memory, at one place it will store the program. You call that one as code segment, and in the same area only it will also store your data, as called as data segment memory. So code segment and memory and data segment memory will be completely overlapping each other. Advantages are obviously to efficiently use the memory. Okay, powerful memory management. Unless unnecessary where it is not required, not to use the physical memory. Okay, programs are very short whenever program and data both can lie in a same physical segment by using the overlapping concept. Okay, like this, there will be total 16 such type of 64 kilobytes locations. At a time, 8086 can access 4 such segments because it has only 4 segment registers. So you can access 4 segments out of 16 at a given instance of time. But always you can change the address written in the segment registers. And suppose here I want to use this particular area at the top here. That means address 00000. So that time I will have to put 00000 or 4 zeros actually in code segment register. Now the code segment will occupy this particular area. Okay, hope my mouse is visible. Otherwise, you can understand the topmost indication here. Yeah. So this side when you use it, you set a 0000 in code segment register. This area of the memory will be used. In this particular thing, you can see IP, whichever are red marked, they are the general offset registers. General for code segment, general and always it is IP. For data segment, generally is SI, and some special cases it can go for DI BX also. For stack segment, SP is general, but in some cases it can go for BP also, like that. All these things will be more clear when we talk about the addressing modes. We have seen segment address and offset address together, how the physical address is calculated. We have multiplied that one with the 10 hexadecimal. That means shifting the whole thing towards the left side and introducing 1 0 digit of hexadecimal onto the right side. Then adding the offset address with it. So finally what you will get is the physical address. Okay. Another example also we have seen it. The top of segment here, upper range, and the bottom of segment here. So that is what we have seen for all our previous classes. So thank you everybody. This is the end of our session today. Thank you.